In this video, we're going to take a look at counting the number of distinguishable arrangements of n objects when we have some objects that look identical, that are the same, that are indistinguishable from each other, but we want to know how many distinguishable arrangements are there. Right? So the number of distinguishable, right, it is clear that this is a different order than the previous one. The number of distinguishable arrangements of n objects where one or more subsets consists of lookalikes. Right? So let's say there's n1 of one kind, n2 of another, n3, and so on. Then we would say, well, if we didn't care about lookalikes, there are n factorial ways we can do that. We can just put them in any order, but sometimes we might have two objects that look identical that have just switched places. And so we've overcounted some of these distinct arrangements. So what we do is we divide by n1 factorial. So how many ways could we arrange the items of the first type? Times n2 factorial, times n3 factorial. Right? All this stuff we are dividing by. So that is our formula. That's the idea. All right, so let's take a look at a couple of examples here. All right. So our first example, let's determine the number of distinguishable arrangements of the letters in the word pipes. So how many letters are there in the word pipes? Well, there's 1, 2, 3, 4, 5 letters in the word pipes. So we'll have 5 factorial on top. And now we're going to identify what's the number of each different type of letter. So how many letter P's do we have? Well, there are 2. So we're going to divide by a 2 factorial. How many I's are there? Well, there's just 1, so we'll divide by a 1 factorial. How many E's are there? There's also just 1, so we divide by another 1 factorial. How many S's? Still just 1. So we have 5 factorial divided by 2 factorial times 1 factorial times 1 factorial times 1 factorial. And when we do that, we get 60 different ways. Excellent. What if we wanted to know how many different ways to order the letters in the word coronavirus? So let's count the number of letters. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. How many letter C's do we have? Just 1. So I'll write this 1 factorial down. Dividing by 1 factorial is just dividing by 1. It doesn't change anything. So I don't really need to write it, but if you want to, we can do that. How many letter O's? Well, we have 2 letter O's, so we'll divide by a 2 factorial. How many letter R's? We have 2 R's. We have 1 N. We have 1 A, 1 V, 1 U, and 1 S. So we have 11 factorial over 2 factorial, 2 factorial. And if we multiply this out, we have what do we get? We get 999. Nope, 9979. 9,979,200 different ways. If we take the letters in the word snowstorms, how many ways can we rearrange that? So let's count the total number of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 letters in the word snowstorms. How many s's are there? Well, there's 3 s's, so we'll divide by a 3 factorial. How many n's do we have? Just the one n. O's, we have 2 O's. W's, we have 1 W. We already counted our S's. We have 1 T. We have 1 R. And 1 M. So we have 10 factorial divided by 3 factorial times 1 factorial times 2 factorial times 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial. And so, if we take our 10 factorial and divide that by 3 factorial times 2 factorial, we are left with 302,400. Excellent. Now we're going to take a look at something that's similar, though maybe a little bit different. Determine how many palindromes, right? So like taco cat, the same forwards and backwards. How many palindromes are there using the letters in Indiana? So let's think about what that looks like. So this is not necessarily using our formula up above. Let's think through. If we're going to have a palindrome, so how many letters do we have? We have 1, 2, 3, 4, 5, 6, 7 letters in Indiana. All right, so we have 7 letters in Indiana. Can we put that letter D anywhere? No, because there's only one of them. So if it's going to be the same forward and backwards, that letter has to go right here, right there in the middle. So we only have one option for that middle letter. What about our first letter? How many options? Can we put the letter I in that first letter? Sure. Can we put the letter N? Absolutely. The letter A? Sure. Right? So we have 3 different options for the first letter. If we put, say, an A as the first letter, right? So let's pretend we've placed an A there. Do you know anything else about where another A has to go? Well, it would have to go at the end because it's a palindrome, so it has to be the same forward and backwards. Right? So that other letter A, it is forced to go as the very last letter. What about the second letter? Right? So if we've already chosen one of these 3 letters, there are 2 options available for this next letter. So let's say that we have selected an N. If that's an N, then back here we also have to have chosen an N. And that leaves just one choice for each of those remaining letters. So the number of palindromes using the letters in Indiana is just 6. Now, the number of different arrangements of the letters in Indiana. So if we wanted to do a question like up above, we'd say, well, we have 7 factorial, then we'd have 2 factorial on bottom 3 times, and then a 1 factorial. And so if we did that, we have 7 factorial divided by this, we would get, there are 630 total ways. Of the letters in Indiana. However, only 6 of those are the same forwards and backwards. So only 6 of those have the letter D in the middle, and then the 2 outer letters being the same, the next 2 being the same, and the next 2 being the same. All right, that's it for section 10.2. We will talk to you guys later.